Hello again. So in the previous two lectures, I've talked a lot about surface potential and what the effect of the surface potential is on the semiconductor itself. Now, in practice, the way we control the surface potential is by applying a gate voltage. That's the subject of this lecture. How is the gate voltage related to the surface potential? So, just to remind you, all of the band bending, everything that happens in the semiconductor depends on what surface potential is. Positive, negative, flat band, whatever it is. But the question now is, what gate voltage produced this specific surface potential? Okay, so to get a handle on that, we will assume again that our wafers, the back of the wafer is grounded. That's our reference 0 voltage. Now, we could do Kirchhoff's voltage law. We could just add up voltages. The voltage across the semiconductor is the surface potential, because it's surface potential at the surface, it's 0 in the bulk. The voltage drop across the oxide, there is some voltage drop across the oxide. When I add those two voltages together, I better get the voltage that's on the gate. Things have to add up. So I simply write this Kirchhoff's voltage law. The voltage on the gate is equal to the sum of the voltage drop across the oxide layer plus the voltage drop across the semiconductor, which is our surface potential. Okay, so we don't have to do any more with the first term, but the voltage drop across the oxide takes a little bit of discussion. The voltage drop across the oxide, well, the units of electric field are volts per centimeter. The units of oxide thickness are centimeters. You multiply the two together, you get a voltage. So the voltage drop across the insulator is the electric field in this oxide insulator times the thickness of that oxide. So we need to find the electric field in the insulator. Presumably we know the thickness of the oxide because we manufactured this particular device. Well, you may remember we saw this expression earlier. The normal displacement field, which would be epsilon in the oxide times electric field in the oxide, should be equal to minus the charge in the semiconductor. That's what we saw from the solution to the Poisson equation. And just to discuss that for a minute, if, for example, I have a metal, and you may have seen this in a course on electromagnetic fields or electrostatics, I may have a sheet of charge right on the surface of the metal. And that sheet of charge will produce a D field that will point away from the charge. And the magnitude of the D field will be the charge density, we usually write rho sub s, sheet charge density in coulombs per square centimeter. And it will point in the minus x direction away from the charge. So the displacement field at the surface is equal to minus the charge contained in that surface layer. So we have a p-type semiconductor, and we have a surface layer, thin layer, we saw that it's only 20 nanometers thick or so of negative charge. Okay? Or it may be negatively charged electrons when we invert the surface. So we have a p-type semiconductor that is mostly neutral, and we have a thin layer of charge at the surface. But it's a negative charge. So the electric field is going to point towards that negative charge. And we can say that the epsilon, if the region out here is an oxide, epsilon in the oxide times that electric field in the x direction is going to be minus this charge because it's a positive number, points in the positive x direction. All right, so that explains this relation here. This is just, sometimes people call this Gauss's law. So assuming that we know the charge in the semiconductor, we can solve this equation for the electric field in the oxide. We can multiply the electric field in the oxide by the thickness of the oxide. Now we've got the voltage drop across the oxide. Now we can also define a capacitance. You may recall that if I have a parallel plate capacitor, that the capacitance is proportional to the area of the plate times the dielectric constant of the material between the two plates divided by the thickness of the material between the two plates. Well, what I have here, I'm going to define an oxide capacitance per unit area. It's the dielectric constant of the oxide divided by the thickness of the oxide. The units are, in proper MKS units, they would be farads per meter squared. We will usually quote them in farads per centimeter squared. So when I do that, I can write my gate voltage relation in a very simple way that I might remember. The gate voltage is minus the charge in the semiconductor divided by the oxide capacitance plus the surface potential. This is just the sum of the two terms. Surface potential, volt drop in the semiconductor, plus volt drop in the oxide. The volt drop in the oxide is just minus the charge in the semiconductor divided by the oxide capacitance. You may remember from your beginning physics or electrical engineering course that charge is equal to capacitance times voltage. That's basically what this is saying. Voltage is equal to charge divided by capacitance. So this is our relation. If we know the charge in the semiconductor, we can relate the surface potential to the voltage on the gate that produced that surface potential. Well, we've seen before how in energy band diagrams, we can qualitatively understand what the charge in the semiconductor looks like as a function of the surface potential. And by making the depletion approximation, we saw how we can quantitatively understand how the charge in the semiconductor varies with the surface potential as long as we're in the depletion regime. So we could take this expression, and if we are given a surface potential, in principle any surface potential, we could determine the charge in the semiconductor, and then we could plug that in this expression, and we could find what gate voltage produced that given surface potential. If the semiconductor is in a depletion region, is depleted, then we already know now how to do this quantitatively. If it's inverted or accumulated, we'd have to think about it a little bit more because we haven't yet developed these expressions for the charge in the accumulation or inversion regime. Now, if we do that calculation, what we're going to find is that as we increase the gate voltage, we're going to increase the surface potential. So it's going to look something like this. Initially, the surface potential is going to follow the gate voltage. The slope of this line will not be 1 because all of the gate voltage does not go into the semiconductor. Some of it is dropped in the oxide, so we lose some in the oxide, and the rest of it is dropped across the semiconductor. Okay. Now, when we hit a critical potential, then we are going to find that when we've bent the bands by 2 psi b and created an inversion layer, suddenly it's going to become much, much harder to increase the surface potential. We'll increase the gate voltage. Down in this regime, the surface potential, the derivative of the surface potential with respect to the gate voltage is less than 1, but it's relatively close to 1. Up here in this region, the surface potential, the change of the surface potential with gate voltage is very small. It's very hard to change the surface potential by much more. The reason that happens is just a little change in surface potential exponentially increases the density of electrons in the inversion layer. That extra density of negatively charged mobile electrons screens the extra charge on the gate so that it doesn't get inside the semiconductor and bend the bands anymore. So effectively, oftentimes people will just say you can only bend the bands by 2 psi b. Actually, you can bend them a little bit more, but it gets harder and harder to do that very much. There's just a small increase in the surface potential as you keep increasing the gate voltage. Now, threshold voltage, we can ask ourselves, when we build MOS transistors, one of our questions is going to be, what gate voltage do we have to apply in order to create a channel? Creating a channel means inverting the semiconductor so that the p-type channel becomes n-type. Or the n-type channel becomes p-type if we have a PMOS device. Okay. Well, we know that we have to bend the bands by 2 psi b. We'll use our expression here. We're going to call this critical gate voltage the threshold voltage. Remember, I'm using a prime here because I have these hypothetical metals that just their Fermi level happens to line up with the Fermi level in the semiconductor at 0 gate voltage. We'll have to fix that later. That doesn't happen in real devices, but it's easy to fix. But for now, we'll use this hypothetical idealized metal. The threshold voltage then will be given by this expression where we put 2 psi b in. So we'll evaluate the charge in the semiconductor at 2 psi b surface potential, and the surface potential here is 2 psi b. Now the charge in the semiconductor, in general, there is a depletion charge. We have a simple little formula that allows us to compute depletion charge as a function of surface potential. And there's also mobile charge in the inversion layer. We don't yet have a formula to compute that, but we'll get one later on. Now, at the onset of inversion, the assumption is going to be at this point, we are just beginning to form an inversion layer. Most of the charge is still in the depletion layer. So we can ignore the mobile charge here, and we can say that the charge in the semiconductor is almost entirely the depletion charge, which we know how to compute. Well, that makes it easy, because since we know how to compute the charge, we know the surface potential is 2 psi b, we now have an equation that allows us, that tells us what gate voltage we have to apply to create an inversion layer. That's V sub t, the threshold voltage. And it depends on this critical band bending, which is twice this parameter psi b, which is easily calculated from the doping of the semiconductor and the properties of the semiconductor, its intrinsic carrier concentration. Now, I just want, before we move on a little bit, I want to remind you just quickly about capacitance. If I have a parallel plate capacitor with some material between the plates with a dielectric constant epsilon insulator, then I can derive the capacitance, and the capacitance is just going to be dielectric constant divided by separation between the plates times the area of the plates, or dielectric capacitance, or capacitance per unit area. I would just divide out the area. Okay, now what happens if I were to have two materials between the plates? Well, this is an interesting little problem in electrostatics that you might take a look at. I'll just give you the answer. The answer is that this behaves as though we had two separate capacitors in series. One that just had the first material between two plates, and a second that just had the second material between the two plates. Right? So that's something you can show with some elementary electrostatic analysis. All right, now let's take a look at what we have in our MOS capacitor. We have a gate electrode. This is a metallic plate. We have one insulating layer here. This is our oxide layer. Okay, that has a thickness Tox. We have another layer that is depleted of mobile charge carriers. It's basically an insulating layer that has the dielectric constant of silicon, or whatever the semiconductor is. And then we have a p-type semiconductor that is heavily or moderately doped, that is almost a metallic plate. So we have two metallic plates, and in between those plates we have two different dielectrics. Okay. So that means that the capacitance of this system is going to be two capacitors in series. The first capacitor is that due to the oxide itself, and the second capacitor is due to the semiconductor. So the first one is dielectric constant of oxide divided by thickness of the oxide. The second one is dielectric constant of silicon divided by the thickness of that layer, which is the depletion layer thickness. Now the difference, of course, is that the depletion layer thickness depends on the band bending. It depends on the surface potential. That's what makes this problem a little more interesting. All right, well, let's use these ideas to see if we can develop an approximate solution to the relation between the gate voltage and the surface potential. This is the exact solution, and it'll give us the right answer, but it can be tedious to solve at times. Now, if we recognize that the MOS structure can be thought of as two capacitors in series, then we can develop an approximate solution. We apply the gate voltage on top. The first capacitor is the oxide capacitance. The second capacitor is the semiconductor capacitance, which is bias dependent because it depends on the surface potential. Our goal is to relate this surface potential, the potential between the two capacitors, to the voltage that we apply on the top, the gate voltage. Okay, now we can do that if we operate below threshold. Below threshold, the semiconductor capacitance is the depletion capacitance. And we know what the depletion capacitance in farads per square centimeter is. It's simply the dielectric constant of the semiconductor divided by the thickness of the depletion region. Okay, so then we can solve for the surface potential with these two capacitors in series, maybe remembering that in beginning circuit analysis we sometimes do problems called voltage division in capacitors. When we have two capacitors in series and we want the voltage between them, the voltage between them is the capacitance of the first one divided by the sum of the two capacitors times the voltage applied across the two. So that's what we have here, a relation between our surface potential and the gate voltage. It's going to be determined by the ratio of these two capacitors. Divide the top and the bottom by the oxide capacitance, and the surface potential is equal to the gate potential divided by 1 plus the ratio of these two capacitors. So it's divided by something that always must be greater than 1. Okay, so we can write this relation as surface potential is gate potential divided by a numerical factor m that is greater than or equal to 1. And that numerical factor is 1 plus the ratio of the depletion capacitance to the oxide capacitance. Now you might ask again, where is the approximation here? What have we done to simplify this exact relation down to something that can be solved? Well, in principle, this depletion capacitance depends on the surface potential. So this equation is actually just as complicated to solve as the one that we started with. But what we're going to do is to recognize that the depletion capacitance varies slowly with surface potential. We're just going to replace it by some constant average value in the depletion region. Then we have a very simple problem that we can solve. All right, I'd like to run through a set of examples here now with some numbers, just so we can get a feel for how things play out. So here are some numbers for a p-type semiconductor, an MOS capacitor. They're the same numbers we used in the previous example. And we're going to see if we can compute this number m and see how big it is. So it just depends on the ratio of these two capacitors. We know that the depletion capacitance is dielectric constant of the semiconductor divided by depletion layer depth. We know that. We know that the oxide capacitance is dielectric constant divided by the thickness of the oxide. We know that also. We plug these into our expression for m. It's just the ratio of dielectric constants and ratios of thicknesses. Put numbers in, and we find that m is about 1.2. All right? That's a typical number that you'll find in practice. Always a little bit bigger than 1. Except for some special structures that we'll talk about later in the course where it's exactly 1. And those are very nice structures. So our relation between surface potential and gate voltage then is that the surface potential is 0.83 times the gate voltage. All right, so this allows us to explain something I mentioned earlier. If we plot surface potential versus gate voltage, in this depletion region, I said that the slope wasn't quite 1. When we apply a gate voltage, it doesn't all get in to the semiconductor and affect the surface potential. Some is lost in the gate oxide. Now, we've seen in this example that surface potential is 0.83 times the gate voltage. The slope here is 0.83, it's not 1. So obviously we'd like to make that slope as close to 1 as possible so that the gate voltage very efficiently modulates the potential in the semiconductor. Now we can also ask ourselves, what's going on in the semiconductor under these conditions, and what gate voltage produced this assumed surface potential of 0.5 volt. Well, okay, so here are, if we're trying to calculate our gate voltage, we can calculate a number of quantities first. We know the surface potential was 0.5 volt. We can calculate things like the depletion layer depth, the charge in the depletion layer itself, the oxide capacitance, and these will all help us relate the gate voltage to the surface potential that we've assumed in these calculations. And we find that the gate voltage is 0.75 volt. It took 0.75 volt to produce 0.5 volt potential drop in the silicon because of 0.25 volt was lost across the oxide. Now we can go one step further and we could ask, if we wanted to invert the surface and create an N-type channel, if this were the channel of an N-type MOSFET, what gate voltage would we need? Well, we would need to find a gate voltage that produces a surface potential of 2 psi b. Psi b is a quantity that's easy to compute if you know the doping density and the properties of the semiconductor, the intrinsic carrier density. We find that psi b is almost 0.5 volt. 2 psi B is almost 1 volt. We have to find a gate voltage that bends the bands by almost a volt in the semiconductor. Okay. Now, before I do that, we could take a quick look at some internal quantities. We know the band bending we might be interested in. What's the depletion layer thickness at the onset of inversion? What's the electric field at the onset of inversion? We can see that the depletion layer thickness now is a little bit bigger than it was in the example when I had a 1/2 volt on the surface potential, because I bent the bands further to invert the surface. So we've depleted a little bit more. The charge on the depletion region is given here. The electric field at the surface now is even bigger because we've bent the bands even more. Okay, so finally, we can put all of these numbers together. We can find the gate voltage that it takes to bend the bands by 2 psi B. We call that gate voltage the threshold voltage, V sub T. We put numbers in, we get 1.28, about 1.3 volts to invert this particular semiconductor. Now that actually turns out to be larger than what you would expect in practice. The reason it's a little bit larger is because we've ignored something which is quite important in practice. We'll talk about that in the next lecture. So just to summarize, our goal in this lecture has been to relate the gate voltage to the surface potential, because the gate voltage induces band bending in the semiconductor. That produces some surface potential. Once we know that surface potential, we can understand what goes on in a semiconductor. There is a simple and exact relation between the gate voltage and surface potential, but sometimes that's too tedious or cumbersome to solve. There is, that exact relation is given by gate voltage is the volt drop across the oxide plus the volt drop across the semiconductor. There is an approximate solution, which is more convenient to use in practice often, where we simply relate the surface potential to the gate voltage divided by a numerical factor that's a little bit bigger than 1. And that term is just 1 plus the ratio of 2 capacitors. And this is a very easy to use expression that we will make frequent use of in the remainder of the course. Okay, so we have related gate voltage to surface potential. What's next? Well, we've neglected a couple of things that are actually quite important in practice. One is I've always labeled my gate voltage as VG prime. I had a hypothetical metal where the Fermi level just happened to line up with the Fermi level in the semiconductor. That's not going to happen in practice. There is something called a metal semiconductor work function difference. We need to account for that. There are some other idealities that can be important from time to time. One is that there may be some charge in the oxide or at the oxide semiconductor interface itself. We will talk about those two important non-idealities in the next lecture.